just to search about this. But remember just to connect with the campus Wi-Fi, and if you use your own mobile device, you cannot download our papers for free. Okay, so our school has been substitute about this core database for us. So let's list this. Okay, so actively explore. So it includes everything about the actively transaction. Let's do. Or you can see the access provided by our campus. So make sure that you are not using your mobile data or your personal network. Okay, so this. Okay, just to search the topics you prefer. So include everything about the smart grid or the power system. Okay. And so you can see there will be some maybe 7 takes here, and I will prefer the journal or the conference. Okay, the journal is I think the journal is maybe has maybe a better qualities, higher qualities than conference papers. Okay, so you connect the journals, and you will see there'll be so many topics. Okay, the applied superconductivities is maybe for the high voltage, and it's not fantastic conditions on smart grid. Okay, and this paper is focused on the demand response. Okay. And if you would prefer some of the specific topics, you can also choose the publication titles here. Where you can say the transactions on smart grid, transactions on power systems, and industrial informatics, and this journal. So you just need to get to this website and to read some of the papers that with the topics that you are interested in, and just to download the paper. Okay, just to, if you prefer this one, okay, so the pure anonymous distributed C, okay, so this can connect image, and you connect this PDF, right, and you'll start downloading. Okay, so this is the paper. And then you just this download, and just on the back click. Okay. So you can just do like this to download your interest paper. Okay. So you have to take notice that everybody should take a 10 minutes presentation. Okay, the PPT presentation from me, and okay, so I'll also give you some advice about how to do your PPT, how to read the paper, or about your topics you selected. Okay. Okay, so the 10 minutes is very short, so that I will suggest your presentation PPT will be at most 20 pages. Okay, and it depends on you. If you either more words or information on your each page, you will take maybe only 10 pages. But if you have so many figures, 20 is okay. But it's up to you. Okay. So, but make sure that you are just doing everything within 10 minutes. We have the 32 students here. Okay, so here is some citations. Make sure related to every page, every presentations related to the topic. Okay. Okay, here are some things of your presentations. When you start to read a paper, so the first thing that about the topic or the significance here. Okay. So the topic is quite simple, right? so what is the paper is writing about, writing for, or writing about, okay? So the problem that will be solved in the paper. So you need to just to emphasize or to make it clear about this since this is the first thing you need to do when you just to read in the paper, okay? So and the second one is that what do you think about the topics? Do you think it's important or not? Okay, it's up to you and you can just to express your own opinions about this about the topics in your paper, in your chosen paper. So, and third one is a bit difficult. So, do you think that is there any other optional solutions for this problem? Okay. Okay. So this GPT I will also send it to the chat group. Okay. So just you can just follow this guidance to read the paper. Okay. So the second one is theory and principles. And so what is the theory of principles is belong to, okay? So domains, optimization, or the doing theories, okay? Then how will these theories and the principles support the solutions that we proposed? So this is the practical implementation or like applications. So is this the hardware or the software? So how the methods that were proposed in the paper is applied in their case study, okay? The first step is that would be, okay, so I think it's the most important, but maybe also a tough step for you because you can just to present your ideas about how the extra improvement about this paper. So although this paper has been published, they are not absolutely flawless, right? So there are also some drawbacks or shortcomings. Of course, and you can just to present your ideas about how to further improve the topics or improve the solutions that were proposed in the paper, okay? So shortcomings, so additional issues, services, and what your opinion about the improvement. So there will be the 4 steps, so following this 4 steps. Okay, so about the presentation, I think there will be the last 2 classes and the 3rd and the 4th classes, okay? So, and the other students, the other your classmates, that will be outside the campus already. So we will just to meet at the Tencent meeting or just some work checking the meeting software for this, okay? So you can just to prepare for this now, okay? There will be more time, there will be more sufficient time for you to complete this. And also I will get some notes, some supports about your communication, also some advices about your lecture, your presentation, also your paper, the topics of paper, okay? I will show you some do you want this? Okay, just doing like this paper, okay? The condition smart grid. So this paper you can say is a smart port location. So you will just to find where the port will be appeared in the computer system, okay? So this is the title of the paper. So we will just to inform you what the topics or problems that we solve in this paper. Okay, and I think the most 2 important parts of the paper. One is the abstract. Okay, so you read the abstract first to know about what this paper is doing. It will tell you, okay, so the first one or two, the first sentence or the second sentence will be what part of this extract will tell you about the problems that we are faced with. So the mid part or the medium part of this extract will tell us about how this paper is solved about these problems. Okay, the final part will tell you, okay, so what's the starting, because they need to take conduct experiment to verify, okay, to verify its proposed solutions. And the second part of and you have, after you have understand the abstract, you should just to skip everything to directly to the conclusions. Okay, the conclusions is tell you what the paper, what the summary is, summary or the output or the consequences that this paper generates. Okay, just to read the conclusions about what is the output of this paper, of these solutions they propose, just to what you can get from this paper. Okay, so the first part and is the conclusion and the abstract. So after you have read these two parts, the third step is the introductions. This is very important. Okay, maybe if you are familiar with this the four locations, the first or two paragraphs you would like to read, but if you are not familiar, you can just spend some time on this, because the first paragraph will tell you, okay, the backgrounds, and then the current researchers, okay? So what other researchers have done for these topics? You can make this, okay? So what's the current optional solutions for this problem, okay? And then the final part of the introductions is quite important. Okay, so the authors of this paper were just to conclude that there will be some drawbacks or shortcomings of the previous method, right? So in the last paragraph, they will tell us what their proposed method is handling this problem. Okay, so I think this paragraph is the third important part of this paper. And then, okay, you can see there is a background about this part. This part will be this formulation of their methods. Okay, the formal part of this paper. You can see, I think it's quite easy because there will be no such formulas here. Okay, quite easy. Yeah, it will be the flowchart of these methods. And actually, and generally, there will be the experiment or case studies in the later part of this paper. Okay. So you can back to the paper in the such sequence. Okay, the first step, topic, the title. Second, the abstract and the conclusion. Third, introduction. And if you feel okay, so this paper is I have interest in this topic, and also I think this method is worth to read. Okay, so then you start to read the main body of this paper. Okay, so the foundation of their methods and the experiment of their methods. Okay. Okay, so let's get started quick go through about these three-phase systems. So, what programs do you have you manage on this three-phase systems? The wide transformation or other? Just like this, because the homework, the first word is about the first two lectures about the complex power and the three-phase systems. So do you have any specific programs, questions about this part, the three-phase systems? Or if you do not know where is the specific your questions, so I will just go back to review the whole part of the three-phase systems, okay? Or so what's your questions about this part? So please feel free to present your questions, because if you do not prepare, if you do not know everything about this part, you have to finish your homework, okay? In the following 2 weeks. So what do you have for some questions? Is there any questions about this part? Or you just need to go through the whole part, okay? Okay, so just feel free to present your questions or problems. The calculation, or you mean you do not know about calculation, or okay, so so you can speak with the previous, okay? So one moment. Okay, so see this one. This lecture too. This one. So this will be the power transformation. The power transformation. So I got your transform formulas in the last lecture. So actually you do not need to memorize that in these formulas. Okay, so even in the homework, I will present you on your homework page, so that you can what you need is just to know how to calculate use these formulas. You do not need to memorize it. So thank you. So you do have the program of this part, this one.
We need this PPT that we didn't get it into.
Oh no, yeah, I mean, so I will have to send all of this to you today.
Okay.
Okay. So if there is no program, so we'll just start lecture 4. Okay. Okay. Of course, if you still have some problems that you do not manage, you can just contact me in the future anytime. Okay. Okay, so the next sections about this process analysis is the transformer line modeling. So we will just learn some knowledge about the magnetics. So have you learned about this before? Okay. So the goals of the sections is to develop a simple model of transmission lines. Okay, so in some part of these sections, it will be much more easily difficult for you to calculate it. So we will just skip that, okay? And we can just take a figure about the geometry of the transmission lines. So geometry is quite important in these sections. and we'll just to see in the later pages. Okay? So the first thing that there will be generally 4 common methods to transfer the electric power, okay? The AC and DC, you know, yeah, water current and direct current, yeah. And there will be overhead. Overhead is just like you just to get in on the road. There will be on the two sides of the road. Yeah, there will be in the open environment. We call it the overhead. It's over your head. Okay. And another form is the underground, just to bury it in the ground. Okay, so we will just to learn about the AC lines in these sections. So it's actually so direct current DC lines will be many advantages about using this. But however, the current color transformer systems in almost all the world is on the basis of the AC power. Okay, so that it will be very expensive to transfer the AC power to the transfer everything, every equipment or devices to the DC powers. So currently only a small part of our transmission networks in our country is processed as DC power. Okay, so it's the common knowledge. So magnetics review. So have you learned in the class of the electromotive theory? Chapter 1, did you do this?
Electromotive?
Yes. Have you learned that? Magnetic force, okay? So, and the magnetic field intensity. You learn about this? You can just imagine it as the electric field, okay? Electric fields. We are also in the electric fields, but we're also in the magnetic and electric fields. So the edge intensity is described how strong or how strong the magnetic field is, okay? So magnetic motive force is quite simple, that is the force is to push or just to proclaim some dynamics. Okay, so as for the magnetic fields, so the existence of the current, just like the current in each transmission line will generate some magnetic fields, okay? So this is one thing. Have you learned about the right hand rule and left hand rule?
Yes.
Okay, so just like, so can I have you, okay?
Yes.
Okay, here is the line, the right hand rule,
Like this?
like this, and like this. Okay, so you are these four fingers is towards the current, because there is the flux current, and will be encircle this direction, and your thumb is towards the direction of the force. Okay, no, this is current. Current. The force you can use this one because this the magnetic fields, the current, and force. Right? The magnetomotive force. Okay, so about the electric force, use your left hand, and if you would like to generate some magnetic direction of the magnetic fields and the direction of the current, use your right hand. Okay, right hand rule, left hand rule. Okay. Okay, so we're just to review this in the later part, in the later page. So exactly, so the stronger the current, the more intense in the field. Okay, it's quite simple because it's in the positive proportion. So another thing that the flux density, right, the P, or just in negative in the Weber. Okay, so the unit of the force, okay, the ampere turns, right? Ampere is the unit of the current. Turns is that how many turns of these transmission lines on this core, this error core, okay? So the magnetic field intensity is the ampere turns per meter, okay? So it measures how strong the magnetic field in the unit unit length, okay? So we have to measure how much the amper turns, how strong the force is in the meter, okay? And about the flux density, so we measure in the Weber or the Tesla or the Gauss, okay? So this is just the unit. So first law, and 1 Tesla is equal to 10,000 Gauss, okay? And it's equal to 1 square meters will be 1 well. So the magnetic field's intensity H is strongly associated with the magnetic flux intensities B and H, will have strong correlations between them. And here is the magnetic flux phi, or magnetic flux here, and it's measured in the Webers. So it's actually the integral. So we have the integral, and differentiation. Okay, the integral of the flux intensity over the surface. Okay, so you need just to have the basic knowledge of this, because we will just have so many examples in the part, the case. And this is the force linkage, lambda, and it's measured in the Weber terms. So if the magnetic flux is varying, such that some you are just to growing and dropping, okay, growing and dropping due to the changing current, because the current is changing, then the magnetic flux is also changing, okay, like increase and decrease, okay. So then the voltage will be used in the conductors. That depends on how much the magnetic flux is enclosed, okay, enclosed. That means that the magnetic flux is just through the conductors, okay? So that what we call the enclosed, or we can just imagine it as a link, okay, at the loops of the conductor according to the thread. Thread is no here, okay? And final parameters is the inductance, right? So because you have the magnetic fields, you will just to induce the inductance L. So we make it in Henry's, because we will be the scientists inventors. The Henry is inventing this inductance. So that's right. The units of the inductance will be this name. So this is the ratio of the flux linkage to the current in the coil, okay? So that will be described how much the unit current in the coil will just to induce small amount or the large amount of the flux linkage, okay? So this includes this the ability to induce the flux linkage. Okay, so just looking at this 1, 2, 3, 4, 5. Okay, just to summarize these parameters here. So the Emerson have the two laws that relate the magnetic motive force, okay, and the magnetic field intensities. So this as everything will just to correlated with each other, okay. So this is the magnetic motive force, okay? So magnetic motive force. So this is the magnetic field intensity. So okay, so it's the vector differential. The differential D is the differential, okay? And this symbol is includes the integration of that, okay? Integration and the differentiation. So this is the integral about the closed case delta, okay? Just about the delta. So the delta here is the uppercase, okay? Uppercase of the triangular, okay? So this is also the delta uppercase, and we have used the lowercase in the previous lectures. So this will be aggregate sum of the current linked by the delta, okay? Just have a look at this. So here's the now just to introduce the line integrals, okay? So it's a general formations about the integrations you see in your mathematics classes with mathematics, okay? So there's the functions, the differentiation of the x, variables x, okay? And here is the integration about this range, from A to B, okay? This integration, and actually the non-integration, so the generation is generalization of the standard integration norm, for example, okay? So this is the standard form, and it's actually just to interpret integration of the functions along the x-axis, okay? Because you can see that the differentiation of the variables here is the x, so that this integration is just to this is the x, okay? This is the function, and the integrations there is just the area of this part, okay? So this is the standard forms of the integral, but there will be another, or be more wide or generalized formation of these integrals like this. Okay, so we just to exchange the x to the L here. So L is the circle, okay? So the general case. This is also the case, but in the more general, so it's in the direct x, this is the only direct lines here, okay? So and L here is the circle that, so that this is also the case that will be enclosed that these integrations here is got to interpret and Flux intensities, Flux magnetic field intensities along this part, along all the paths, okay? So it's actually, we have just to explain the application of the standard forms of the non-integrations here. So that you can see the inverse also is very useful in the case of symmetries, right? So this line is equal to symmetries. Okay, so that is the circular pace of the radius x. We assume that this radius of this circle is x, okay? Radius, you know, x. And if it is known well, so that the h, the magnetic field intensity, and the differentiation of this part of the I will be the parallel, okay? So that the intensity here will be, you can say, is a constant number. It will keeps unchanged, okay? So, and the differential issues here is integral to the, you can see it's very simple because the length of this circle, okay, so it will be 2 times x times pi, okay? So, like this, right? 2x and times pi is equal to the minus of this. So that's how we calculate these integrations here. And so next, we're just to discuss down the Flux intensities. So if there is no permanent magnetism, okay, there will be only the transmission well and the arrow cores here, so there will be no permanent magnetism here. So magnetic field intensities H, okay, so and the Flux intensities are raised by the permeabilities of the medium, okay, so H here is the magnetic field intensity and D here is the Flux intensities, okay. So in the linear magnetic materials, for example, so the arrow cores here is the linear magnetic materials, and inside the medium, so every magnetic field will just describe, okay, by the distribution band or say the bandage, okay. So this is what we call the linear material. In that case, Okay, we can see that the flux intensity were equal to the mu times h, right? H is the magnetic field intensities, and we call the mu is the permeabilities. It's just a coefficient, and mu is equal to the mu zero times mu r, right? So mu zero is the permeability of the free space just in the L. Okay, and here's the exact value of these variables, mu, and of course everything will be present if we have the program about this in the homework or in the examinations. Okay, so 4 times pi times this, let's say the quite small, right? The permeabilities in the air is quite small, okay? And for mu r, it's the relative permeabilities, okay? So, so mu r is 1 for the air, okay? So this free space is not in the air space, okay? So the free space means in the space there will be no such things, even no air, okay? So no other substances in this free space, and this mu r is the relative permeabilities for the air. Okay, so it's actually mu is equal to the mu zero times 1. Okay, we have to assume it is equal to 1. So the magnetic flux, okay, so the magnetic flux vapors and see the flux densities, and you can see something about those units, okay? So the vapors divided by the square meters, okay? So you can see why it is called the flux densities, right? It describes how the density of this flux in this unit space or in unit areas, okay? In unit areas, 1 square meters, how many vapors here? Okay, so in that case, we can just define the magnetic field, right? B, we interpret the flux density B in the area of through the first A, right? Because the B here describes the unit flux or the density flux in unit area, okay? So it's a big interpret here because, and so there is a differentiation of the A, the vector, the direction, normal to the surface, okay? So of course we will have some assumptions to make the calculation of the flux density B more easier, okay? So we'll assume that the B is uniform and perpendicular. Perpendicular is for the vertical, okay? So 90 degrees surface, and here is the flux, okay? This is for the perpendicular. So that you can say it's simple, right? Just use the density B times the whole area A equal to 5. Okay? And is some magnetic field from the single one. So there's examples, okay? So we assume we have the infinite non-while current 1000 ampere, okay? And consider there will be a square of the square is here, right? It's a rectangular but with the same mass, okay? The mass of this is set, and okay, between the 4 and 5 meters from the well. Between this, here is the line, okay? Here is the area we were focusing on, right? 1 meters, and this square is maybe the distance between this square and the line is 4 meters. So make sure. So this line and the square in the same surface. Okay, you can just see there also in this surface. This is line. We can just to place this line and the squares in here. Okay, in the same surface. And for this, okay, so this is the curve range. According to the right hand rules, this is the curve range, and this is the direction. You can see this four cylinder is the direction of the magnetic field intensity, right? Doing this, and you can see some of them will just do flowing out and here, flowing out and here. Okay, some of the flux will just do through this area. Okay. Yeah, you understand? Okay. So this square and line will be the same surface. Okay. So we need to calculate how much the magnetic flux passes through the square. Okay. So here the flux from the out of the spring and the inside spring. Okay. We have to calculate how much the square can receive power from the action. Okay. So the direction of the magnetic field intensities should be left-hand roll. So the left side of this noise out of the spring and the right side of this noise were inside. Okay, out and in. Okay. So the easiest way to solve this problem is to take the advantage of symmetries. Okay, so we can just use integration case, radial s, because we have a circle, right? We have a circle with a radial x. Assume here is a circle, and here is a circle. It is a half circle on this screen. Okay, another subcircle whereas behind the spring. Okay, so can you imagine there's a circle. Okay, we assume here is a circle. Okay. There's a circle, and we assume here is a circle with a radius of 4, okay? Here is the 4, okay? And the circle draw 5, so there will be 2 circles, right? So in that case, we can just use these 2 circles, the difference between the 2 circles to get the difference of this flux, this magnetic field intensities, okay? So there will be the flux, so there will be the flux pass through the square, okay? So the circles x will be varying from 4 to 5, okay? Because here is the 4, and here is the 5, or is 1 and 5, okay? And make sure that the wire is in the center of the circle. So when you have the integration of these magnetic flux intensities, right? The dl is the length of this circle, right? And circle, we could see that this is the radius, right? Radius x, so that you could see the length of the circle, it should be 2 times x and times pi, right? Because this is the length of the circle, okay? So, and x here is from 4 to 5, okay? It's actually, so we are going to calculate a ring, right? You can see here the ring. So, this is the hollow in the 0 to 4, but there is the ring from 4 to 5, right? We have a ring is here. It's like a ring, okay? The hollow in the center part. So then the first step, so there are 2 times pi times x and times h here, okay? So we place the edge outside of the interpolations equal to the I edge. Okay. Okay, so here is the formation. So the magnetic force, yeah, is the integration of the magnetic field intensities, and here is the current here, right? Okay, enclosed current, enclosed current. Enclosed current means, yeah, here, the current is in the line. Why we said enclosed the current, okay? So the current is enclosed by the ring. So that H is equal to this, okay? So from here to here. And then the flux intensities is equal to the mu 0 times H, because mu R is 1, okay? So we assume that this ring is in the L, okay? So have you do you remember this? Yeah? Mu R is equal to 1, so it's actually mu is equal to the mu 0 directly. Unless there will be specific assumptions in the questions. Okay, so H is equal to this. And we can calculate, because mu 0 is equal to the 4 times pi times 97 square of the 10, okay? And mu 0 is here, okay? And quickly add this. So from this step, you understand this step.
How long do you have?
Here to here. Oh, this is the first one. It's a unit. Okay, so the blue for you. Okay, so from density 1 liters per square meters per Tesla and 10,000 Gauss. Okay, so it's only that's the unit. And the flux, you can say that the definition of the flux, yeah, is the total flux, that magnetic total magnetic flux phi, okay, is the integration of the flux intensities. The integration of the flux intensities here, right, is only called the 1 meters for this. It's actually, okay, so you can see that is the area of this ring, okay? Area of the ring. So the range of the integration is from 4 to 5. 4 to 5, yeah, this one is 4 and 5, okay? 5 to 5. And B is here at mu 0, I, the target, is 2 times pi x here. And for this, and mu 0 is a constant value, okay? So we have to take it out. Okay, I divided by 2
by 1.
pi, because you can see that we are just to focus on the x, because this is only directions, okay? 4 and 5 with the x, right? So that only the vector x is the input variables. And you know how to calculate this. And that's the L and X. Here's the differentiation. Yeah, 1 by x, or just the E from X to 1x, 1 plus x. 5 minus 9, 4. So, okay.
Yes, sir.
And so this is equal to 9, 5 divided by 4. So you understand this because 9m minus 9n is equal to 9m divided by n. So this is
ln is log over.
yes, of course, this is in the math. Okay. So here, watch the current is 1000 amperes. Yes, Q pi, Q times pi below, mu zero below. So 1.25. Use your calculators. Okay, calculators, and you can get the force right here. So this is magnetic force causing the wheels. So, any questions or problems here? So, it's actually, I will tell you, this calculation is quite simple in other this metric, so that some of the calculations in the later part will actually be in practical. Okay, so we're just going to discuss later. Okay. So here's the Flux linkage, red small, okay. So Flux linkage, okay. So V is the linkage, is the voltage, okay. Lambda is the Flux linkage times T, okay. So per is the differential of the lambda plus linkage to time, okay. So Flux linkage, so it's actually introduced how much Flux in linking n per coil. So this is the coil, right?
Yes.
So it will be 1, 2, 3. Okay, so it will be 3 terms here. Okay, 3 times coil. So the lambda should be the sum of the n turn coil with each coil. Right? Yes, this is one coil. Okay, one coil is the Flux linkage. The Flux magnetic force linkage would be the phi, okay? The phi. So see, when the linkage, Flux linkage is caused by the 1, the first, the second, the third coil. So this Flux linkage is indicate the sum of this magnetic flux that will be pass through the whole coil, okay? So the 1, 2, 3 will be like this. So will be the sum of the phi. So it's actually just n times phi, okay? N is the number of the coil. So in final step, so the darkness, so for medial magnetic systems. Okay, so then Flux intensity is equal to the mu equal to the h, right? H is the magnetic field intensities. C is the Flux densities. Okay, so mu is here. Mu r is equal to 0 in L, so only mu is equal to mu 0. So C is equal to mu h. So actually we can define the inductance. Inductance is the L, right? Inductance. So to the content of proportionalities relating the current and the Flux linkage. Okay. So the lambda, the total Flux linkage, total Flux linkage is equal to the current and the inductance. So inductance here is actually means how much flux can be generated by the same amount of the current. Okay, if the inductance is high, the value of the inductance is high, so only the same amount of the current can generate much more flux linkage. Okay, it's been the ability to generate the current to generate the magnetic linkage, cross linkage, okay? So here L is the carrier, okay? If H is different from this. Okay, so I will tell you something outside this our synthesis, okay? So when you read your paper, you will see the H and the standard H, right? So this is for the constant variables, and this is for the variables. And if this value of the variable can change, you can write down like this. Okay, so or you can usually if the H is units or a constant value, constant variables, you can use this direction. Okay. Okay, so summary of magnetism, yeah, you can understand. So the first thing, the current of the conductors, okay, current of the line conductors here. So the current of the conductors, we can use this. If your right hand rulers, you'll be encircled, okay? So the magnetic field, the magnetic bars were encircled the line, okay? The current I here, current, and we can go to calculate the magnetic force here. Magnetic force here is equal to the current, the closed current in the multiple terms, okay? The terms is the integration of the magnetic field intensity H here, okay? So integration of the H. And the third step is that the H and here, okay, so the H times the mu, the coefficient, right? Mu equal to the mu0 times mu1. Remember, so mu0, mu1 is mu r is the relative permeability, so it will be 1 in the L. So we can just calculate the Flux densities, at least the permeability times the magnetic field intensity, okay, permeability, the magnetic field intensity here, okay, Flux density. And Flux density can be used here, and if we calculate the integration of the Flux densities here in the area, okay, the A in the area, so the surface integral of the Flux densities, you can see, we can get the Flux Flux, magnetic flux, that magnetic flux in the only one term here, okay? Yeah, magnetic flux Y is only for one term here. And for the n terms here, so just to multiply Y times the n, okay? The Flux, total Flux linked by n term here is the lambda Flux linkage. And not that, so inductance is equal to the Flux linkage divided by current, okay? So is there any questions or problems for this part? Have you learned this about this magnetic field in this program class? Yeah, so everything's okay? Okay, so I'll show you about the next. So we will have the three before we start the next presentation. So I will show you some yeah, it will be a bit more difficult to calculate. And okay, so even in the semiconductor case, so I was not sure how to just to prove or just to get these equations. Yeah. And for the non-conductor in this case, we can just use this number. Okay, so that's what we call the boundary. Yeah. 1, 2, 3, 4. 4 lines in one position. 4 stops, 2 lines, 4. Well, you can use this matrix, and we'll just use some assumptions here. So you can use the boundary inductance, okay? Anyway, so let's have a break, and we will meet at 10 o'clock, okay? Yes. Okay, so this is the substation box. Let's see. Okay, so the interface old-fashioned because this photo is taken before the 15 years. So,
Box network.
yeah, anyway, doing the box substation box like this. Okay. Okay. So I'll give you another examples of the inductance. So we will have to recognize this. Okay, so we will calculate the inductance with the N turns coil wonder technique on the error core. So this is the error core, okay? The error core is in the circle. So this is the well, this is the coil. Okay, so N turn coil run on the error core that has the radius of the R, okay? Radius of the circle, the R. And cross-sectional area, so it's the cross-sectional. Cross-sectional is actually, so it's doing like this. Yeah,
Cross-sectional.
understand? Yeah, cross-sectional. So this is only to show you also this is the cycle. So assume that the all bars is within the coil. So here, so is no bars outside the coil, okay? So the second one is the all bars being in return. So that's why the test will be the bars linkage times the N is the total bars, okay? So the third one is the radius, so it's turned in a geo compared to the radius R, okay? Okay, so in that case, we'll assume that the radius of each turns is measurable. So the radius of the coil will assume that it is 0. Okay, so because it's a very small compared with the R. Okay, so you can see because this is the current, right? This is current downward, according to the right hand rule. So this is the flux, right? This is the flux, just we made this at the counterclockwise. Okay, so this is the circle force delta of the radius R, which is at the quarter. It goes over the N turns of the coil, and hence so the enclosed current is equal to the N times the I for each current, so the current for each coil, okay? The first thing is the enclosed coil, so I will remember this one. Yeah, this is the interval of the magnetic field intensity H, yeah? So that the N times I, so time times so this is the total enclosed current, okay? So if Q times r, right? 2 times r multiplied is the mass of the circle times h. Okay. Here's the case 9. 2. Let's uncast that. So in that case, we were just to place this 2 pi r here in the next step. Okay, just to write down, please. So it's actually from this formula, from this equation. So add varies some word with r. Okay. And the next step is we determine to reach the Flux density. Flux density equal to the mu, the permeability. Permeability is the relative permeability and phase value and relative permeability equal to approximately 1. Okay, 1 to the L. So mu equal to mu0 times the h. Okay. So we assume we have to assume that this is the medium magnetic material. So next step is phi equal to the A times B, where A is the area of the cross section. Okay. Phi area times the flux densities. Okay. So next step, so lambda the flux linkage, total flux linkage is n turns back, n turns coil. So for the phi, for each coil, so the lambda is equal to the n times the phi. Okay. So the lambda is also equal to n times A and B. So the everything I have here. Okay. So the final step you can try to get the inductance. That inductance equal to the lambda by the current. So it's kind of easy, right? Okay. So I would suggest you to have a look at the last page of our previous lecture. Okay. So there will be a step. There will be step by step to show you how the order of these parameters comes from. So okay, just following the steps then you can just solve all the questions. Touching? No. Okay. Okay, so let's continue to that. For inductance of the single wire, okay, so let's consider, so okay, the first and the simplest situation is the single wire, okay. Well, and if we do develop a model of the line, we need to first need to determine the inductance of each phase of the wire, okay. Single wire, definitely a non-wire. So to achieve this, we have to determine the wire's total flux linkage, right? So in the transmission line models, so we have to consider two aspects of the total flux linkage. The flux one is that, so this is the wire, okay. One is here, okay. So the flux linkage inside the line, and another one is outside, okay. So inside and outside. So this is equal to these two aspects of the total flux linkage of this wire, okay. So we also assume that the current densities within the wire is uniform and the wire is solid with the radius of r, okay, so the previous assumptions. And in fact, the current density is non-uniform in the real applications, okay. So the conductor is strange, so solution will be approximate. So anyway, so if you are in the real applications, thing. You take your oven, you can take all the oven more complex method to calculate. However, in our class, we're assuming this is the ideal environment. Okay. Okay, so the flux linkage. So the first thing we were to learn about to look at the flux linkage outside of the well. Okay, so we're outside the well. So let's just to take this model or these assumptions and this model system like this. So well at the second loop closed by the end turns that a return well is equally far away. Okay, so we're assuming that this line, the single line is equally very, very, very long. Okay, so here and with the radius is r. Okay, which is radius r, and therefore lambda is equal to 5 because there is only one term for your there is no multiple Fouriers here, multiple transformers here. So the flux linking to the mass of the well outside is to the distance of r. So what is the r? The uppercase r here, we assume that is the farthest range that the flux can spread. Okay, so there is no flux outside the uppercase r. Okay, this is the assumption. So it's the farthest range, the north range, the flux can spread. Zero flux here. Okay. So in this case, we will see that because the current enclosed is equal to the integration of this magnetic field density. Okay, so and here, so this is the previous numbers we learned that we have learned this. The flux linkage of one term flux here is equal to the integration of this flux densities in the area of this area. Okay? And we assume that here is a very tiny unit directions or very tiny unit mass here. Okay? Here is actually there's so many axes here that you here this range from the 0 to the uppercase r, right? The 90 as here. Okay, and for this, because you can see this is 1 meters here, okay? Because we are just calculating the unit parameters. So we assume all the parameters is equal to all the flux is generated by this only this line here, and the length of this line, the wire is 1 meters. Okay, so this is 1 meters, and so these areas we can calculate is the differentiation of very tiny the x times 1. Okay, so let's divide the mass here. Okay. And so here is the integration range from the r, the lowercase r to the uppercase r, right? The lowercase r, that make sure that outside the well, okay, to the maximum range, the health, the max range of this flux is right. So r to r, so here, okay, and of course the density is equal to this, okay. And say B right is equal to this, N is equal to 1, okay. So mu R is equal to 1, okay. So we're going to do this B and this, okay. Understand? Have any questions? Okay. So the lambda is equal to simplify because there's only one term here, one term for here, so here, so here. So since the length of this wire is infinite, okay? The length here is here, okay? We assume it's 1 meters here, but actually the wire is infinite, so we're just to deal with the percentage. So we as well assume to be the per meter, to 1 meters for this wire. Okay, so lambda divided 1 meter is lambda per meter equal to this. The mass is 1. Okay, the mass is 1 here. The integration, the mu 0, integration of this, and can you remember how to from here to here? You understand?
Yes, sir.
You understand? Because the x
1 by x is dx equal 1.
yeah, the line x, line r minus line uppercase r minus line lowercase r, and this. Okay. Okay, so you can see this quantity is positive proportional with r, right, uppercase r is here. So next step, okay, so you can see that the outside proximity is very easy to calculate. However, we have to calculate the inside of the well, the proximity inside, okay? So tend to travel on the outside of the conductor with the spin effect, okay? So this page is talking about the real applications, okay? So the penetration of the current into the conductor is approximated using spin physics, okay? That means in the real applications, some of this is the ideal environment, okay? So all the bars were traveling inside the conductors, but some in the real applications, some of them might be outside, okay? So let's take a look at this. Okay, so you need pictures like this, the thing is, the F is the frequency, and Flux here is the conductivities and seconds per meter, okay? So let's look at this. So for the copper spin is equal to the 0.33 inch at 60 hertz. So the durations will assume that uniform current densities, okay? So just to look at this, it could be very useful, but only when it is used in the real applications. So okay, so for our assumptions, so this is the cross section of the lab, okay? So this is the error color or cold color or silver color. Anyway, so this is the color of this and this screen of this lab, okay? So we assume that this the radius of this color is the x, and radius of the whole well is the lowercase r. Okay, so these are our assumptions. The current enclosed within distance, so x from the center here, okay, equal to, we can generate that equation that the encircles, because we are focused on the inside the cross linkage, okay? So that means the encircled current is x squared divided by the r squared, that times the total current, okay? Total current, because we assume that the current, you can say the current densities is uniform. It's our assumptions here, so we can just use this positive positions, operations, and this. So you can see these magnetic field densities for in this part, the coil, right? So the coil is equal to this. Remember this, right? And n is equal to 1. And you understand that why is the square of that? Because the area is x squared times pi. The area is the x squared pi, okay? So it's actually the ratio of the area of the small circle and the large circle, okay? So hx is equal to this, and use this here, so we can just get the value of, I will get the expression about this density, this magnetic field densities inside this coil, okay? So you can see that this situation is a little bit more difficult than the opposite way, because the flux only means part of the line, okay? So the lambda instead, lambda here is the flux linkage, the flux linkage is equal to the integration of the flux density. Flux linkage is equal to flux density, right? How do you contrast? Yeah, lambda is equal to the integration of the flux density, right? Okay, so in this area minus this density, so we will use this. So the mass of this wire times the integration from 0 to lowercase r, right? Integration to the lowercase r, right? Mu and the permeability is times here the h, right? The h here minus times here, right? Because B, the flux density is equal to the mu times h, right? That, let's say the mu h okay, so from this we can just calculate, because it is only about the differentiation about the x, right? So we can just do so we have just to place to take all the constant variables outside the interface, okay? L mu 2 times pi, 2 times pi, r, the whole square of r, right? And the charge. That's good. So do you know how to calculate this?
Yes, sir.
That's good. Yeah, because the differentiation of the x, the whole square of the x is equal to 4 times x cubed, okay? So that 1/4 x minus 4 equal to 4. Okay? 4 okay. Then okay. 4 times 2 is h pi. Okay, so this is the denominator. So denominator mu is equal to mu 0 mu relative times I is minus. Okay.
But my result there is integration of x cube. So integration of x cube is x cube 4 over 4.
Yeah. And the unit r, right?
But how can you find this 4x cube? I think it's no need.
This one. Yeah.
This is differentiation, I understand that.
Yeah, differential. Yeah. So should be forced to here and 3.
I understand, but well, I think we know it this one. So I do
Okay, so I mean, so just back continuing like this. This is differentiation of this one because y force here is a constant. Like constant is not variables. Okay, this is equal to this. Okay, so what is this? Okay, then. Okay, so because we have to calculate this one, yeah. This square this, square of this x. And then for this part, okay. So because this is the differential of the area, okay. So that's why we just use this. This part is equal to this, okay. So we convert the differentiation of the area to differentiation of the x, the radius of the x. So it is the ratio of this area of this cube circle. Okay. Which one?
square divided by r square.
This one? Because you can see this is the differential of the area, right? It's actually, so this is the ratio of the areas. So because we would like to convert this differential of the area because the area is very difficult to calculate, right? Okay, so this is the area of this circle. The x square of x is the area of this. Okay, so the dA will convert to this part, dx. Because x is much more easier to calculate integration.
Are you ready?
Okay.
N mu I over x calculation. I do this x cube, so this is x cube by 4, and the I4 and close. So this
Yeah.
2 by x,
X.
5, I over x, L.
Yeah, okay. It's good, right? Just we have to be doing like this output. Okay. Okay, so in this case, we're getting the total net loss. Okay. So you see, this is Flux inside the line. This is the Flux outside the line. Just add there, okay? Flux outside the line, add the Flux okay? We can just write here like this. So that lambda is equal to L times I harmonic, okay? So we just to delete this, divide the harmonic, we can get the unit inductance of the one single well of the parameter, the unit of the inductance, okay? So we're doing this, okay? So this is the outside of the well, the plus outside the well, the plus inside the well. Take them up. Okay. Okay. Any questions up here?
This logic is second line. Where is mu 0? Yeah.
This lambda? This two?
Yeah, yeah.
This two?
mu common mu by 2 pi I common
Let's say. Because we can get the output of the function. So this is the flux inside the well, okay? This is flux, and this is the flux outside the well here. So we can just do add them up, outside the inside the L, okay?
mu common
Why would the mu are relative here? Because if inside the well is not in the L, right? The mu r for here, because it's outside the well, it's in the L. In the L, we will assume that, okay, you can see
the mu common
this mu r, this should be a mu r here, or mu r here is equal to 1, because in the open air environment, it's outside. But inside the well, it's not in the L, okay? So that mu r is not equal to 1. It could be in the arrow, in the copper, in the silver. So in that case, those days, the mu r is not equal to 1 anymore. Okay, so last step, we have to simplify this inductance. Okay, so we know this. 9a and b, 9a times d, and 9a minus 9b is 9a divided by d, and this, we get this. And this is our previous fractions here, okay? We can just write down here. This is equal to the A rash, so it would be the mu r divided by 4 is actually this, okay? And this mu is equal to the 9r minus 9r, okay? Understand? Because this should be the positive mu r divided by 4, but we assume that okay, minus mu r divided by 4, okay? So 1 minus here, okay? So this r should be minus mu r divided by 4, and minus is equal to the positive, okay? Q negative is equal to the positive. Not negative. So negative. Okay. So this step, this two. mu r point 4, right? This part is equal to 9 uppercase R minus 9 lowercase r. Okay, this is this. And 9 uppercase R minus 9 lowercase r minus, can use this third equation, okay? 9 natural exponent, okay, natural exponent 4 mu r divided by 4, okay, so that 9 uppercase r minus this 8 this, okay. For these, we can use this equation slash r add this 9 lowercase r add 9 this is equal to r times this the exponent of minus mu r divided by the 4 as the component of this natural next exponent, okay? From here to here, it will be this first formula, okay? Understand? Okay, in that case, we assume this part, you can see very complex, okay? We assume that is r plus, lowercase r plus, so that the 9 uppercase r minus this is equal to 9 uppercase r divided by the r plus. This very simple, okay? So we will just to call this uppercase r the effective radius of the conductor. Okay? So it's actually if the mu r is equal to 1, this effective radius is approximately 0.78 of the original radius. Okay, simplification. Okay, so we will just do the look about this and have maybe n conductors here, 1, 2, 3, 4, 5, and P conductor will have the car range of the IT, okay? The range in some specified geometry, so this is only for expressions, so I think it's the not symmetry expressions, symmetry locations, okay? We have to find the last leakage of each conductor. So each conductor last leakage, right? For like this, it depends on its own bearing and the bearing in all other conductors, right? This is the third inductance for this, and also the mutual inductance. This have all just to affect this one, okay? Okay, we can look at this. Like this, the P1, right? We assume that the directions of these P's, the conductor to the conductor 1 is P1P, okay? And also we assume that this R, uppercase R1 is the maximum range of these P conductors. Okay, that's you that need to know. You can know that the lambda for the conductor 1 is expressed like this, okay? So this what we have learned about in the previous page, that this is inductance of the single well. So it's actually the third inductance. That is the inductance generated by the conductor itself, okay? And then matters B12, B13, B14, here the B1N, okay? B is the direction of these two conductors, right? So the three conductors, and then we can write down like this. We can just treat these expressions into two parts. The first part is that for this, okay? The second part is for this, because we know that 9 R is 1 divided by 2 is 9R minus the 9R plus 1. Okay? So it's one part and the second part. Okay? So if we assume that the R1 is the infinity, we assume that this directions, because in real world, okay, so there will be many wells in one transmission lines. So actually, we were just to like this well, okay, 1, 2, 3, 4. There will be 4 lines here. So actually, the directions of this each line is quite small. It's negligible compared with this, the maximum range of the spreading of the flux, okay? So that we will assume that the maximum range of the flux will be infinity, because we assume that this one is almost 0, okay? Compared with 0, so the maximum range will be infinity, okay? Okay, so in that case, the R1 equal to R2 equal to R3 equal to R4, so everything is okay. So everything is in the same value. So, okay, so this second term from the bottom can be written as sigma. Sigma, the sum of this current in each set, in each conductors times the line R1, okay? Okay, so just have a look at this. I don't know if this one will be your conditions, but to understand the three-phase transmission lines, I have to show this to you, okay? Just know this equation or this formula exists, or you write down of this. Okay, so if we are starting a balanced three-phase or maybe micro-phase systems, yeah, we know that the current, the sum of the current will be 0, right? You understand? Do you remember that future current is 0, okay? So this one is 0, okay? So this one is 0, this one is 0, this one, the second term is 0. We have assumptions so that the flux linkage for the first conductor is equal to the first term back. The first term right here. This is to write down like this, okay? L11 it means the third inductance of the conductor 1. The L12 it means the neutral inductance between the conductor 1 and conductor 2. Okay, so we have to define a cycle or expression of this part except for the current, okay? you can see the serve and neutral inductance, so that if we have a balanced three-phase system, so this neutral inductance can be cancelled because it will be 0 at the stem, okay? So the current system like this. Let's say some will be cancelled. Yeah, this flux negation will be equal to 0, okay? So it's not at this one in the balanced situation because three-phase system is the symmetry system, okay? In the symmetry three-phase system, this neutral inductance can cancel. So we only need to implement the third inductance. Just doing like this, okay? Okay, so here is symmetric line spacing for this line below, let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, okay? Okay, so I will give you one example, and we will finish this our learning about our study in power system analysis. Okay, so this is the example. So yes, this is the balanced three-phase system. Okay, A, B, C with equal direction between each two conductors in the uppercase D, right? Okay, so these diameters. The radius of this each well is 1.24 centimeters, okay? And the length of this transmission line is 5 miles, okay? So in the balanced system A, B, C, the current is this reference to the sum of the three current equal to 0, so that we can express like this A current by the phase B and phase C, okay? And use the equations, the formulas in the previous pages, okay? So this is the third inductance, this is second, and this is the neutral inductance, okay? From B and from C. Right, we are going to use the base A as the representation. Okay, this one. Okay, so substituting these equations, we can get to calculate this. B and C, okay?
Like out putting scouts in the color.
And this is equal to minus, okay? Minus A, so that we can get this one, okay?
Should be revisable.
Yeah, because we can just use this. The current in the base A is the same in the B and C. Okay, because we are in the symmetry system, three-phase system. So 9 this minus 9 this equal to 9 this. Okay. So this is Flux energy of the conductor A. You can get the inductance of the conductor A, okay? Just to divide by the current in here. This is all values, D, the meters. The R magnitude is 0.78 centiAh, okay? there you have for the radius is 1.0 or it's very important number to calculate the growth percentage. Okay, so anyway, to take every values into these equations, you can get the value. Okay, maybe for the base A is equal to 1 following this value. Okay, every parameters. And converting this to the reactance, okay, so
Inductance to reactance 2 pi L.
okay. And for the capacitors, okay, so this is capacitors. 2 times 5. Okay, so here is the system in the United States, so it will be the 60 meters, okay, times the inductance, and the reactance is to be 0.7798 ohm per mile, okay. Maybe for the 5 mile lines, it should be 3.79 ohm. So that's why we have learned that there should be a loss in the on the transmission lines in the real world. Okay, so you can see only for 5 miles it should be almost 4 ohms per phase. Okay.
Total for 5 lanes.
Okay. So why is we use the phase A only for the total 5? Okay, because there will be no mutual inductance, because we know that this is in a symmetry, 3 phase systems, the mutual inductance can be cancelled. Okay, so we will stop here because it's maybe quite difficult to track. Okay, so we just to have some time to calculate the whole cell of the smart grid. Okay. Yeah, because y is R1, we assume that R1 is infinity, right? Because the directions between each conductors in the real world is quite small. So we assume that the speed is equal to 0 compared with the R, right? So that in that case, the R1 will go to the infinity, right? In that case, we just assume that the average will be in the same value, okay?
But I said about 1 by R1.
This one,
No, not this one. In the up here. Long, 1 by R1. Yeah.
this to this.
Yeah, this one, 19 and up here.
Okay, you can come back.
Okay, this 1 by R1, long 1 by R1. After and
Oh, this is 9, after this 1, like this, 9, or minus 9, this. Right? just to rewrite it as a minus, but it's okay because the same term will be zero. So the add zero or reduce zero is okay. You could say that here is things the line R1 plus the respective R1 times R1, okay? The respective line R1 respective R1 A line R1, okay? So here to here.
They just using long A by B where A minus D.
Yeah, of course.
This root.
Because UT continues because the continuous is 1 divided by the R divided by 1, so it's okay because anyway you can also use the R1 minus this.
This is also okay.
It's also okay.
If I use minus, so this my result is divided by 2 pi. I1 log R1 minus plus I2 log R2 plus IN log Rn minus A0 2 pi I0 R1 if I use minus there, log mu naught by 2 pi log R1 plus, so the minus I1, R1 is up. If I use minus there,
It's okay because you can see
if I
the
use
first thing that you can say is you can divide by you can to times the sum of the current, right? The current here is equal to 0. So that no matter what expression you use, the second time will be 0, okay? And you get the first term first time by doing the different, using the different expressions.
yes, sir.
But why we do doing like this? Because this is the definition of this.
Yes.
Okay, so we are just to define this expression other than this, okay, to the third inductance. So it's just this condition, okay?
Yes, sir. So if I use by around plus this is just long A by B
Yeah, your solution is also okay, but actually,
but this is the definition.
Yeah, so we have to follow this definition. Yes, because everybody in numbers is doing like this, okay?
But different way you going to see this.
Yeah, but if you can define your expressions as another L plus 1, it's okay. Yeah, but it's up to you. Okay, so let's get something more connecting, easier. So let's just to finish maybe another 30 or 40 minutes I would prefer just to finish this wholesale, okay? So in the previous lectures we will see the commutations, okay? So the third step is the data head and then leading up to the operating hours, okay? So it's actually the plane of this aircraft, how to conduct the plane's data. So there will be 5 steps. So congestion, revenue rest, okay, to the market, reliability, unit commitment, and the just period to the real-time operations. So there will be 3 steps in this data head and the meeting up operations before the real-time operations. the first one is the day-ahead market, okay? So the day-ahead market is actually one that makes interval program is for the optimizing, over the horse energy fees and offers, so that we are just to decide the settlement price before the day that you were to sell or to buy in your energies, okay? So what we learned before the day-ahead market, it is the 24 hours ahead of the operation days, okay? So the second one, the objective is to maximize the fee based the values minus overpaid cost. It's actually like this, okay? So the fee based the values is that, okay, so here is the big, something like this. Here is the sale price, okay? Offer price. Yeah, you could say that this is the bid price. It's the offer price. Offer price means you sell your own electricity generated by your generators, okay? The bid is that the electricity utility buyers to purchase the electricity from your generators, okay? So there will be multiple buyers and multiple sellers, that in that case some of the sellers will present the high price and some will present the lower price, okay? Also, so does the bidders, okay? So then how to get the settlement price in the day of the market? Actually, this point, maybe this is $1. This is $1, it is $10, and $5, okay? When the offer and bid is two lines will intersect at one point, so this should be the settlement price. And in that case, all of these electricities sell or purchase in the day-ahead market should be with the price of $5, okay? So for the monitors, generators, he provides the offers that if you set your price for $1, because you have a very quite a relatively lower cost, okay? Cost, you get a profit rebate. You can see there will be a revenues, okay? Revenues here for $4, but if your cost is much higher, because for example you have spent $6 per megawatt, okay? So this is only for the instance. $6 per megawatt, you will to lose $1 per megawatt, okay? So that's why the day-ahead market is doing to maximize this revenue. Actually, this is the amount of the electricity, the price, okay? So the revenue of this is the area like this. This is the bid, it's over. So you can see the objective is to maximize the revenue minus over basic cost. It's doing like this. Okay? This area to maximize the area of this. So the market is voluntary but officially binding. So you could choose whether to attend the day-ahead market or not. Because you could imagine that all my electricity will be worth more in the spot market. Spot market is what is that maybe 1 hour before, or we will start to send out our power to say, okay, so these generators, I know, or I can forecast that it's one of these generators we are out of work tomorrow, so I will keep all of my power or order at the reserve, and so I will not attend the day-ahead market today, but tomorrow I will send it to him at a very much higher prices. Okay, so it's the voluntary. You can choose to attend or not. So execution is at 10 a.m. and it's at least 2.5 to 2.5 hours to post. Okay, so this is the execute time. Okay. That's one thing I want to contribute to you. Do you know what is the congestion in the power grid?
One.
Congestion?
Wholesale market?
No, congestion. Congestions in the power grid is not for the wholesale, right? Do you know what is the congestion? Imagine you're just driving to the downtown at 5 p.m. So what will you make? What situation? So do you think that there will be a very empty road for you to drive, or there will be many vehicles to pack together?
Empty road?
At 5 p.m. Right?
Oh, AM is many people. I think
There's a lot of 5 a.m. is packed.
Everyone
Right?
together from the office.
Okay, so that's like the road. Okay, so congestion is also the situation that, okay, so existing the generations, actually the existing generations cannot meet the requirements of the consumers. Okay, so that the consumer of the nodes will require 100 megawatts. However, all of your generators can only produce 90, so that you will be average of 10 megawatts. Okay, so this is for the congestions. That's why I think I will give the examples, because the 5 p.m. is the high demand of the road. Okay. So everybody will prefer to go back home. So it's just like electricity, and there will be 18 to 19. So everybody will be going back home and turn the conditioners, turn on the televisions, so that the load demand will go very high. So that at this time the congestions, the power grid congestions may appear, or very likely appear in the very likely appear during this period. Okay.
Like a bus ticket.
Yes, bus ticket, or so that in our power systems there should be which should be a target or the requirement for our power system operations, N-1 or N-2, okay?
Yes.
N-1 means N means the load or the parts of the power systems that bring these three. A very simple three-phase power system, right? N is equal to 3 here. N-1 means when the phase A, B, C, the A box A is out of work, and there is a sufficient reserves or other operations at B to tuck in here to make sure that the system can operate in a way as long as one node is out of work. So the -2 is 2 out of work. So it will be much higher requirements for the operations in the power systems. So that if you read papers, there will be a lot of papers researching on this N-1 to keep the reliability of the power systems. And here is one of the most important criteria to evaluate the reliability of one system, M-1 and M-2. In that situation, if your systems can also goes well, okay, so your reliability of your systems is as well. Okay, so the data head will be using average from the December, so will be how many bids and offers. Okay, so we can see that 30,000 bids, but 1.5 thousand bids and offers, and 203 part offers. You will see there will be the bids and offers crash frequently in Texas. Okay. So the transactions can be optional for you for the bidder or the offers. Okay, so one multiple or all hours. So you can choose your own transactions. Transactions is that the payment, or you can see the payment of your money. Okay. So that for the architect, because he is in charge of this whole operations of the transmission network, okay? So they need to take control of the reliability of the transmission network to make the N-1, N-2, or it should do something to avoid the congestions of the power transmission network, okay? So that he do over some transactions. Transactions here can be the payment or also the power. Transactions to power, okay. So to make sure that the transmission, the limitations of the transmission lines will not be reached or not be seized too much, okay. So that you reach commitment, plus changing topologies. So all is the optional behaviors or countermeasures for the potential market or for the potential congestions, okay? So this is the computing unit for this process. So that you can see that the number of transactions get much higher from the 2016 to the 2018, right? So leading up to the operating hours. So in that case, maybe there will be operating hours is almost past here, so that information comes usually it comes ahead of hours before the operating hours, before the real operations, okay? So generally includes the combined forecast, okay? So the source, operating plans, fees, and offers. So the network topology information, the historic and current grid conditions, okay? So the topology information, you know what the topology is in the network, okay? Topology, right?
Network topology.
And this is quite important when you use that to. So, do you remember that the problem, the questions you asked me in the previous lecture? Do you have this? Let me see.
The delta.
This, okay? Yes.
Yes, no.
Yeah, this is negative. You could say this is not a data, right? This is not a data. This is not a data. I'm going to here, okay? It's not here is not the data nor the Y connection. So the topology of this network is much more complex than we can say. We can solve it using our knowledge of our previous lectures, okay? So in that case, we can only use the Y matrix, not the maintenance matrix. So the Y11, Y12,
Y13,
just that there be somewhat similarities among the surf inductance and the neutral inductance, right? Y11 is the surf inductance, Y12 is the neutral admittance between these two. Okay, so we're going to discuss this later in the following lectures, so that the topology of the network is very important for the operations of the system. Okay. So how the information is used? So there will be three aspects. The first one is the reliability unit commitment, and the supplemental ancillary service masks. So the auxiliaries maybe we were to discuss later. We have sufficient time. So the third is the power operation data, the power flow, the state voltage stability, the short security ratio analysis. Okay. So we were just to focus on the first aspect, the RC, the reliability unit commitment. So the RC is a process performed by ERCA to evaluate whether there is adequate resource reserve capacity to meet the expected demands. It's actually RUC is deployed for the potential congestions, or just to say that to meet the requirement of n-1 or even n-2 situations. Okay. So do you know the answer to these questions? So the QSE is the distribution of the system. Okay, so do you know? Can you remember this? QSE is here. Yeah. Not here. Qualified scheduling entities. So QSE is actually the control the generations, okay? So if the QSE has started making operation decisions for your own resource fleets and updating their own plans, so the system has what it needs to meet the forecast for energy demand without having the contested issues. So what's your idea? What's your idea about? Do you have any idea about this? What do you think? Does the system has or not? No?
No. Doesn't. What it needs to make focus for energy one of the transmission.
So do you think you know? Yes or no? Just guess. Just take a guess. 1 or 2 or yes or no? Okay, so actually the answer is no. Okay, answer is no. So because there will be no forecast, you can say then there will be no forecast within this archive. So archive is
Without this transmission.
yes, because the archive is actually not charged in this for the forecast. RUC, so the general philosophy of RUC to net the market in the commitment decision. And they are almost lead so that the archives do not charge for this, okay? So the process is also using the multiple in various inputs. So the archive is also attempt to send some information or instructions, combination of the instructions as much as possible, okay? So let's see this. So this is the start of the day, 1.1 a.m., 2 a.m. until the 18 p.m., okay? So this will send this necessary, and you see, so the now to commitment will send in each hours, okay? From 0 to the end of this next day to here, that's the day 2, okay? So the period means 0.0 a.m. in the second day, okay? In the 1, the 2, so every hours include until the 23, the home for 1 hours, okay? Okay, so you can just take a look about this. So there will be a great number of the contingencies. Contingencies means maybe some generators, including some generators that work. There will be some outages in one transmission lines. Okay, so there will be a large amount of number of the contingencies appears every day. So when needed, so the circuit will be identified at least for solutions. Okay, so what we have learned that what we need to know to control the circuit breakers of the transmission network. Okay, when a small part of the systems where there be some problems, that something wrong happens in this small areas, we need to open the circuit breakers, to make sure that only a niche area of the range of the problems that to be handled with the whole system. Okay, because we will find the least code solutions here. So why is what the RUC is doing? So the process may be primarily occurs in the day ahead and hourly. You can see the last step 1 day before, okay? So 0 to the day 2 and hourly. So at each hour, the RUC will conduct solutions for all the potential contingencies, okay? Maybe for every solution will take 10 to 15 minutes. Wait, like this rounds when 14 will be a contingency here, okay? Okay, maybe 10 to 15 minutes. So ancillary services, the sense that services are provided by the market participant to support a very reliable electric power. Okay, ancillaries. Okay, is of course the reserve of power is one important type of the ancillary service. Okay, ancillary is to back up some powers. Okay. So in order to be used for, you can see the potential system disturbance. So our generators, trip or sudden, forcing change in demand. Okay, so demand may change, generators may change, everything may change during the day. So why the ancillary services or relative reserve is important. Okay. Okay, so we're just to continue to the fourth part, the real-time operations. Okay. So the stage estimations, you have not learned about the stage estimation of the power system. No? Have learned about the stage estimation of the power system. Okay. The estimation is actually to estimate the operation, the state of that operations in the power transmission network. Okay. So that it's a very important topics in the power system analysis. We can see that it is over 1,000 lines conforms or the associated circuit breakers, switches, everything in the power transmission networks. The stage of everything you need to find a method to get a correct estimation. Okay. So it will be very hard or challenging topic in the recent period. Okay. So that state estimator it also helps to identify errors. So it's needed because you find some bad states or some normal states, there might be very likely potential errors in that place or in that switches or in that places or the part of the transmission network. Okay, so that the state estimation will come back every 5 minutes. So the real-time contingencies analysis, okay. So maybe you can say that executing the power flow studies. So we were just to study power flow studies for the very simple topologies, very simple systems with very simple topologies, okay. And for the large scale systems, the power flow is much more complex. And for the Urge, they were executing the power flow study for almost 7,400 contingencies, so that it won't be an easy work for that. Okay. So the thermal and voltage concerns. So we have learned that. Okay. So it's the most two important feature of the transmission line limitation. Okay. Whether the transmission line, the voltage is not be too large of this limitation, they will not, the thermal is not too, not very hot to get something bad to burn down, to burn grid and grid the transmission lines. Okay, so the thermal and voltage concerns. Okay, so the thermal is that you have also the real-time operations where you introduce some resource sensitivity information for the constraints. Constraints means the thermal and voltage concerns. Okay, here's the same things. And also the potential congestion issues will be evaluated for every 5 minutes. Just like this. Okay, so there is operation of the system. Yeah, the task. Let's say with analog access and some more signal. Here is a more signal. Okay. Okay, so the equations, the resource meter is used to simplify all sources to solve the dispatch limit constraint. Okay. Stretch complex. So first that we will have to get more repeats as we can, but we have to follow the constraint of each transmission lines. Okay, just like this. That's why we call it dispatch. The economic dispatch, but we have to obey the strict laws of the transmission networks. So this will execute every 4 seconds. So with the real-time operations, we will also evaluate the local market competitiveness in 5 minutes. Okay. Okay, so I can have a take a look at this. How fast is that? Okay, so we have 5 minutes. Okay, then we have to finish our class. So let's take a look at the constraint dispatch. Okay, so if you have learned something about the power market, it's good for the economic dispatch. Okay. So this is real-time operations, I can say. Okay, so anyway, have the last holiday, but remember to finish your homeworks. I will give you 2 weeks, okay? So 1 week for fun, and 1 week for only 10 questions, and some postage to quite simple, okay? Okay, so you could just do handwriting or by typing, it's up to you. And it's okay, it's up to you. And handwriting, you can just to send me a photo, or you can just to bring it for you. You can just to grab me. You can just grab it to me directly, okay? So all the lecture notes I will send it to the group chat, okay? And for the lecture 5, so the transmission, the magnetic, and some of the difficult parts, so we will not add them to the examination, okay? But you need to get a basic idea about it. I know, just like this lecture 5, we know that the 5 bonds, we know the 3-phase system, the magnetic, we know how it is. You do not need to memorize how to calculate it, but you need to know how this process is done. Okay. Okay. See you next week.
Next week.
Okay, see.